Okay, now we're back again, continuing from where we left off in our last video. I think we went a bit overboard with the time, so I'm gonna try to be a bit quick on this one. So now, going back to similar shapes. Now, what I said before was similar shapes are shapes which are alike but not necessarily identical. Now, let's say we were to look at these two shapes. At first glance, they just look like the same thing. No, not the same thing. They look alike. Yeah. So in geometry, to say these two are alike, we have to look at two things. Are the interior angles corresponding with the interior angles of the let's say this is my figure A and then this is my figure B, right? And then what I'm saying is they have the same size of the corresponding angles. Now looking at A and W, they both have an angle of 105 degrees, right? Z and D both have 120, and Y and C have 90, and then X and B have 45, right? Which means they have the same size of corresponding angles, all interior corresponding angles, right? And then the second thing you have to take into consideration is the ratio with regards to the lengths of the corresponding angles. Now, this basically means if I were to take W and Z and take its corresponding side, which is A and D. Now, if I was to say AT divided by this thing, W and Z divided by Z and Y, right? And do the same thing on this side, divide this 8 by this 4, right? I'm supposed to get the same ratio to say these things are truly similar shapes, right? Now, if you punch this 80 divided by 40 into your calculator, you're going to get a ratio of 2. Same with this side. If you say 8 divided by 4, it's going to give you 2. You can also use like any sides that you like. You can say 4 over 15, but now if you say 4 over 15, it means on this side you must say 40 over 150, and then they're going to give you the same ratio. And then if they give you the same ratio, you can say with confidence that these two figures are similar, not the same, similar. And then let's go to this one here on the right hand side. I'm going to call this figure 1, and then this is going to be my figure 2, right? And then looking at these markings they made here, they're showing us that this angle is equal to this angle, and then this angle is equal to this angle. Same with these ones. This one is equal to this one, and this one, right? And then by that, it means it satisfies the first definitions, which says the same size of all corresponding angles. And then looking at the ratio thing again, sorry. If I were to say I'm doing the ratio of this side and this side, and I'm taking the ratio of this side and this side too. Now, if I were to say I'm dividing this length by this length, I were to get a ratio of 1 over 2, right? And even on this one, if I were to say 2 over 4, oh, my 2 doesn't look nice. Let's erase that. And then we're going to say, probably write it a bit nicer right now. 2 over 4. Now, if you use a calculator or you do your workings with your genius brain, you're going to see that 2 over 4 simplified is basically 1 over 2. So it means the ratios of these sides, the corresponding sides, are the same, which qualifies the second statement we made, that for us to consider shapes to be similar, it means they must have the same size of corresponding angles, which they do, and they must have the same ratio with regards to the corresponding sides. And therefore, to say 2 over 1 it was going to be 2. If I were to say 4 over 2, it was going to be 2, 2, right? Which means their sides have the same ratios. And now another point of what you need to look at. Let me start with erasing everything here for the diagrams to look nice again. Right. Looks a bit clean now. Okay. What you can notice from these diagrams, both these diagrams, 1 and 2, and this one and this one, right? You can pause this video and think about it. This diagram looks like this diagram, but now it looks like this diagram on a larger scale, and this one looks like this one, but now this one is shanked to this one, right? Now, in similar shapes, the size doesn't matter. What matters is the size of the angles and the ratio of the corresponding sides. You can also have a diagram which is more like this one, right? Which means this, and this are gonna be similar too. Yeah, so that's all you need to know about similar shapes at this stage. And then we're gonna move on to types of triangles. Now, in the types of triangles, we have 4 types. We have scalene, isosceles, equilateral, and the right-angled triangles. Scalene triangles are the triangles which don't have any equal sides or equal angles. For instance, the one we're looking at, let me change the color, the one we're looking at in this figure. The markings here show us that all these sides are not the same, because you have 1 strike, you have 3 strikes, and then you have 2 strikes here. So it qualifies as a scalene triangle. And then in this second one, we have 2 sides which have the same strike, which shows us that this side and this side are equal. And by definition, an isosceles triangle has 2 equal sides, which means this one is an isosceles triangle. And then an equilateral triangle has all equal sides and all equal angles. And this triangle has 3 same markings, right? So it means that this one is an equilateral. And by intuition, by seeing the equal, you think of equal, right? Yeah. So that's basically the idea behind it. And then a right-angled triangle has a 90 degrees on the corner. Now it can be orientated in any manner. It can be face down or faced up, but as long as it has this box at this edge, it means it's a right-angled triangle. And that's basically all you need to know about the basics of Euclidean geometry. Hopefully on the next video we're going to be doing more of some calculations and some practical stuff to apply the theory we've learned about in the past video and this video. Yeah.